So, in the previous lecture, we saw that given a topological space, given a locally compact topological space, space X, if it is not compact, then we can compactify it. Right. So, what did it mean by saying that we can compactify it? It meant that, so we can construct a compact topological space X X hat, yeah, such that X is sitting inside X hat as a dense. So, recall that when we say compact topological space X, in our definition of compactness, we need, when we say compact topological space X hat, in our definition of compactness, we need X hat to be Hausdorff, and we had proved that X hat is Hausdorff as a dense subset, as a dense open subset. And in fact, X hat was obtained is just X disjoint union a point P naught. Right? So, there is a picture we can keep in mind while we, so let us take the real line. The real line is locally compact, but it is not compact, and we can take this point P naught over here. So, when we compactify the real line, let us see what we get. So, instead of making the picture like this, we will make the real line like this. Yeah, and this point P naught is here. Right. So, recall that there were two kinds of open subsets. One kind was type A open subsets. These were open subsets of X, right? And the type B open subsets were as follows. We take any compact subset of R. So, for instance, we can take this union of two compact subsets of the real line. So, that is going to be compact, and we just take the complement here of compact subspaces. Complements in X hat. Of compact subspaces of X, yeah. Or in other words, what we have specified is what are the open subsets. The open subsets which contain P naught are exactly complements in X hat of compact subspaces of X. Okay. So, in the same way we can see another example of R2. So, instead of making our R2 like a plane, we can make it as a sphere. So, from this, in the picture it is clear that one point compactification, it seems that of R should be S1, right. And similarly, if we take R2, okay, so I should make a dotted line, right. So, this is our R2, and we can imagine the point P0 over here. So, R2 is also a locally compact, and therefore, we add this point P0. So, the one point so what are the neighborhoods open subsets which contain P0? These are the open subsets of type B. So, these will be, we can take any compact subset of R2 let's say this is D. Yeah, so then D will be somewhere over here. This D, and we just take the complement of D. Yeah, so this x hat minus D. Okay, so yeah, so it's useful to keep this picture in mind. So let us begin today's lecture. So let's write down what we proved last time. Let X be a locally compact topological space which is not compact. Okay, then there is a compact topological space X hat along with the inclusion I from X to X hat such that X hat is just if X union a point which we call P0. I is continuous. I of X is an open subset of X hat. I of X is dense in X hat. Okay, so let us make the following easy remark. Note that I from X to I of X is a homeomorphism. Right? So we have already seen that I is continuous and the image of I is lands inside I of X and it's a bijection. Yeah. So we have already seen, or we know that I is a bijective continuous map. I is a bijective continuous map. Right. So thus, to show that I is a homeomorphism, it is enough to show that if U contained in X is open, then I of U is open in I of X. Right? But now note that I of U is the same set U, and as U is a subset of type A, is an open subset of X hat of type A. This implies that I of U is open in X hat, and as I of U is contained in I of X, and so also in I of X. Right? So thus I is a homeomorphism. Okay. So this theorem we had proved last time, and in the previous lecture I had mentioned that this particular one-point there could be many compactifications of a locally compact topological space, but this particular compactification has a very nice and special property, so which is what we will see in this lecture. So the topological space X hat has the following property. Okay, proposition let T be a compact topological space which contains X as an open subset. Okay. So, what is the meaning of this sentence? Right. So, this means that there is an inclusion J from X to T. It's an inclusion of sets such that J of X contained in T is an open subset and J from X to J of X is a homeomorphism. Okay. So, there is a inclusion such that, let me also write J is continuous. Okay. So, then there is a unique map. So, what we have is we have X over here and we have this inclusion J. J is a continuous map from X to T and the image. So, let us say the image is J of X and this is a subset of T, right. There is an open subset and we have this map like this, and we also have the map I also satisfies these properties, right. There is X hat, there is also open and X hat, right. So, then there is a unique map F from T to X hat. Is a unique map F from T to X hat such that the following two things happen. F compose J is equal to I and F of T minus J of X is equal to this P naught. So, X hat has this point at infinity which is P naught. Okay. So, let us try to see what this means by means of an example. So, let us say X is this open disk, right. Okay. Right. And let us say I embed the open disk into this closed disk. Right. On the other hand, the one point compactification, this is J, this is I. The one point compactification looks like, so I have to add a point at infinity, so it will look like something like this. So, okay. Yeah. So, this point is P0, right. So, what is F doing? F is collapsing all of the boundary. F so F collapses the set t minus j of x, which in this case is this black boundary, right, to the point p0, right, and f is completely determined at other points by the condition f compose j is equal to I. Okay. So, we want to say, so this in this example f does this, but okay. So, let us say that, let us try to prove this proposition, which is that there is a unique such map f. Okay. So, proof. So, of course, f is continuous. There is a unique continuous map. Right. That is the assertion. So, proof. So, the map f has been defined set theoretically on all of t, right. So, this map has been defined set theoretically on all of t. So, how do we do it? So, on j of x, define f to be, so just j of x. J is a homeomorphism from x to j of x, so we apply j inverse as x and then we apply I. So, this goes to I of x, right. This makes sense as j from x to j of x is a homeomorphism. Right. And okay, so we don't need homeomorphism right now, so we just need bijective, is a bijection. Right, we just need bijection right now because as of now we are really trying to say that f is defined set theoretically, right. And outside on t minus j of x, we have defined f to be the constant map p naught, right. So, thus the map of sets f is completely determined, right, and so it is unique. So, we only have to show that f is continuous, right. Okay. So, for this, so let V contained in X hat be an open subset, right. So, let us first assume that P0 does not belong to V, right. So, in that case the open subset is contained somewhere over here, right. So, okay. So, then it is easily checked. This is an easy trivial check that f inverse of V is completely contained inside j of x, right. So, as a result, so this shows that f inverse of V is actually equal to f restricted to j of x inverse of V. Okay. Now, notice that, so note that f restricted to j of x is from j of x to x j inverse, and this composed with I to I of x, right? And as j from x to j of x is a homeomorphism, this implies that j inverse is continuous. This implies that I compose j inverse is continuous. So this implies that f restricted to j of x is continuous. Right? So this implies that combining these we get that f inverse v is equal to f restricted to j of x inverse v, which is open. Right? So thus if P0 does not belong to V, then f inverse of V is open. Right? So now let's consider the situation if P0 belongs to V, then x hat minus V is compact, right? And contained, once again, contained in I of x. Okay. So once again, f inverse of this, since it is contained in I of x, is equal to f restricted to j of x inverse of x hat minus v, right? But this is a compact subset of I of x, right? And this set is in fact equal to f restricted to j of x is equal to I compose j inverse, and both these are homeomorphisms. So this is from j of x to x j inverse, and this is to I of x, right? And both these are homeomorphisms, so this implies that f restricted to j of x is a homeomorphism. Right? So which implies that f restricted to j of x inverse is a homeomorphism. It's continuous, we just need continuity. Right? So this implies that f restricted to j of x inverse of x hat minus v is a compact subspace of j of x, and so also of t, right? So this shows that f inverse of x hat minus v is a compact subspace of t, and so also a closed subspace of t, right? So this implies that, but f of x hat minus v, f inverse of x as f inverse of x hat minus v is equal to t minus f inverse of v. This implies that f inverse of v is an open subspace of t. Yeah. So this proves that f is continuous. So this completes the proof. So we will end this lecture here.